Hello everyone, we are talking about 6.3 notes over binomial and geometric random variables. Our EQ is how do you determine the type of random variable being used and calculate its probabilities. So we've talked about normal random variables so far, and we've talked about what makes something normal. And usually we'll say that it's normally distributed in the problem, or we just have assumed that it's normally distributed up until this point. But now we're going to talk about a binomial setting. In a binomial setting, if you think about like something being binary, you have zeros and ones, and so you have two different outcomes. Okay, so a binomial setting calculates the number of successes out of a total number of trials when performing several independent trials. Okay, and we have four different conditions. These are our bins, is what you have to remember to look for. So you have, if it is binary, so the result of a trial can be classified as a success or a failure. So if it was flipping a coin, heads would be success, tails would be failure. That is binary. There are two outcomes. Or if it's making a free throw shot, they either make it or they don't. Or if something has the probability of occurring or not occurring. There are two different outcomes, okay? And you can classify one as a success and one as a failure. All right? And they don't have to be 50-50, but there is a clear definition of success or failure. The second thing that we look for is independence. So if it is independent, knowing the previous trial's result does not change the likelihood of the next trial. So if you know that you got a head last time, flipping it again does not change the probability of you getting another head. But like, think about like if you're flipping cards from a card deck, if you flip the first card and then you go to flip the second card without putting the first card back in, the probability has changed. Okay, so the likelihood that you get an ace after you draw the first one and it's an ace, that changes because now we only have 3 aces for 51 cards. But if you put it back in, then the probability does not change. Okay? Number is the n, and you are going to decide on how many trials before you start, and then you have success. Okay, or not, yeah. So the probability P of success is the same for each trial. So the probability doesn't change, which we already kind of talked about when we talked about it being independent. So capital X or capital Y or whatever you decide to call your random variable is going to count the number of successes 0 to n. N is the number of trials. And so if you have like 10 trials, you either have 0 successes, 1 success, 2 success, all the way up to 10 successes. And so that's where we're going to go from there. All right. So P is the probability of success in any one trial, and you can find the binomial coefficient, so the number of ways of arranging k successes among n observations. So if you have 5 coin flips, let's say, and you want exactly 1 head, well, you could get exactly 1 head on the first try, or exactly 1 success, so 1 success on the first try, or it could be on the second, third, fourth, fifth. And so, but if you had 2, then 2 heads out of 5 flips, then you could have them both in a row, or you could have them the first and the last. So this is how we figure out how many different ways you could get that number of successes. So you say n, choose k, is how you pronounce it. And n, this is what we call a factorial. And that just means, like, if it's 3, it's 1 times 2 times 3. If it's 5, it's 1 times 2 times 3 times 4 times 5. You don't have to remember that for this context. I just want you to be aware of that, because we can use our calculator and use the combination menu 5-3, which gives you n, choose, or combination r, is how they have it set up on the calculator. But it's the same thing as n, choose k. And this is what we will probably use a lot. Okay. So the binomial probability formula is the probability of x equaling k successes is out of n trials, this many successes, the probability to the number of successes you want times 1 minus the probability to the power of the number of trials you have minus the number of successes. So let's take this example, and you can use this calculator setting. So menu 65A will get you there. But it says biologists estimate that a baby elk has a 44% chance of survival. Suppose researchers chose 7 baby elk at random to monitor. Let X equal the number who survived to adulthood. Find the probability distribution. So let's say that you want to find 0. Then out of 7 trials, we want 0 different successes. And the probability of each success is 44%. We're going to raise that to the number of trials we have. We have 7. We have 1 minus 0.44 to the 7 minus 0. That's how we have it set up. Alright. And if you type that in on your calculator, just like that, you would get that. But you can also go to menu 65A. And we have N trials. Here's 7. The probability of success is 0.44. If you want to find a certain X, so if you wanted to do 0, you could type it in there, or you can just leave it blank and it'll give you, this is going to be 0 successes, 1 success, 2 success, 3 success, and you end up getting this probability distribution here. So it'll automatically give it to you, and then we're going to come back and calculate these in just a second. Okay, so if you want to add the probabilities of less than or greater than problems, so like what's the probability that more than 4 elks survive into adulthood? Well, that would be 5 adults survive, 6, or 7, if we have 7 different to choose from. So you would go to menu 65B, and you would need to write it like this on the test. So the number of trials we have is 7. The probability of success is 0.44. The lower bound would be 5, and the upper bound would be 7. And if you type that in on your calculator, you have menu 65B, and you would type in 7.44, and then we have 5 and 7, and you find that it's 0.140. Okay, and you could also have taken it from our probability distribution and just add the 3 different probabilities that we're working with, and it would work out to be the same thing. Now to find our mean, we're just going to take, for any binomial distribution, it only works for binomial distributions, you're going to do N, so the number of trials, 7 times the probability, 0.44. So we have 7 times 0.44. So our mean is going to be 3.08. Okay, and then for our standard deviation of the random variable x, we're going to do the square root of 7 times 0.44 times 1 minus 0.44. So it gives us 1.313. Okay, there we go. And that's how easy it is to calculate your mean and your standard deviation. Alright, you can also use your calculator for that. But if you've noticed, though, if you think about elk, it's a little different than what you thought we were going to be dealing with. But for most real-world sampling, we don't have replacement. You're not putting back that elk that either lived or died and then seeing if it lives or dies again. So, meaning once something is chosen, it's not put back into the mix to be chosen again. So binomial conditions are not met. However, if the sample is less than 10% of the population, 7 elks is going to be less than the 10% of the total population of elks, we can use a binomial distribution to model the count of successes. And so as long as lowercase n is less than or equal to 1 over 10 times capital N, or the total population, it meets the 10% condition, and we can use a binomial distribution. However, as n approaches infinity, so as our sample gets larger and larger, the binomial distributions appear approximately normal. And so we can use a normal approximation when the number of trials times the population is greater than or equal to 10, and the number of trials times 1 minus the, did I say population? This is the probability, sorry. 1 minus the probability is greater than or equal to 10. And this is called the large counts condition. And if that condition is met, you would find it using your normal probability table, just like we have with our mean and our standard deviation, and going from there. Geometric random variables. The geometric setting is similar to a binomial setting, but instead of counting the number of successes, you count the number of trials until you reach one success. And so y, our random variable capital Y, is going to be the number of trials, and p is going to equal our probability, or the probability of success on a given trial. Now the key is you must have failed all previous trials. And so think about, like, if you were going to flip a coin and you would count how many trials until you reach exactly, until it flips to a head, would be an example of a geometric setting. And so if you flip it the first time, that's a 50% chance you get it the first time, and then so on and so forth. And so this would be our equation that we use to find the probability. You can also use menu 6.5e to give you a single probability. So the probability that you get like 5 failures and then 1 head would be, you would type it in and use 6 for the trial number that you were on. So okay. And then if you wanted to find like a bounded, so the probability that you get a head within the first 3 flips would be 6.5f. Okay. To find the mean of your random variable y, it's just 1 divided by the probability. And what we're going to do in here is we will not be finding the standard deviation of geometric probability distributions, just because it's beyond the scope of this course. Now, if we think about it like a coin, the first time you flip it, you have a 50-50 chance. Alright, so say that's 0.50. Well, the second time, like if you get it on the second one, so you failed the first time, that's a 50% chance you failed, and then you get it on the second time, then that means you have a 25% chance that you get it on the second flip. And then you would see that it keeps going down and down and down. And so you see that this is always going to be a right skewed shape when we're dealing with geometric random variables. And that is going to kind of sum up our 6.3 notes. I will post pictures of this as well, but hopefully this will be helpful to you.